Hey y'all, in this lesson we're going to be looking at symbolic logic and negation. This leads very nicely into truth tables, which will be my next video. So typically speaking, when we're looking at symbolic logic, we use letters like P, Q, R, and sometimes S to represent statements. So, I guess technically you could use any letters here, but these are probably the most popular letters that you're going to see. And then we have logical connectives, which we talked about in the previous video, and those are and, or not. I don't think I put not in the previous video as a connective because it's usually at the anyway, but we do have a symbol for not, so I have it in the table. The symbol for and is an upside down V. The symbol for or is a V, and the symbol for not is kind of this little squiggly, tilty, I guess you would call it. The type of statement for and is called a conjunction, or is a disjunction, and not is a negation. So those are just kind of some basics of the connective words, and we will be using letters and symbols instead, because that's kind of what symbolic logic is. We substitute those for full statements. So I have some examples here. We're letting P represent the statement, she has blue eyes, and we're letting Q represent the statement, he is 6'3". We're going to translate the following. So in the first example, we have P and then this symbol Q. So this is just a symbolism for the statements that we have above. And so if we were to write this out the longer way, we would have P, which is she has blue eyes. And then the symbol V is or. And then Q is he is 6'3". And that's all. And then this is, since it's or, this is a disjunction. And that's all at once. I want y'all to try this one. Pause it, try it, come back. So for this one, you should have she has blue eyes and he is 6'3", and this is a conjunction because of the and. One of the things that I kind of do as a memory device to help me when I was learning symbols was this little upside down V kind of looks like an A, a capital A. So that might help you differentiate. And if you know and, then you know that or is the other one. So that might help. Okay, and then we have another statement. This little symbol outside means not. This little symbol right here means or. So if I were to translate this into words, I would say it is not the case that she has blue eyes or he is 6'3". And this would be a negation. We will learn in a later lesson a different way to translate this using De Morgan's law, but for now, we'll just go ahead and leave that as is for this lesson. Go ahead and try this next one, pause it, try it, come back, check your work. So in this one, you would have, it is not the case that she has blue eyes and he is 6'3", and this is just a negation. Okay, a quantifier, quantity, if you think of the word quantity, means the number of. So quantifier is describing how many, basically. How many or how much of an object, we'll just say. An object or a case, we could say. Oh, cases. Whoops. Okay, and then to negate quantifiers, you kind of just have to find the opposite. So like in the inequalities, if it was not less than, then that means that it had to be greater than or equal to. So we're kind of doing that here a little bit too. The opposite or the negation of all do would be that some do not. or even not all do. And then the opposite of some do would be none. And then the opposite of none would be some. So basically with none do, to negate that, you would just have to find one, kind of like counterexample, you just have to find one that exists that does. Anyway, so those are the negations for those. If you see those in a statement, then to negate that, you would say these. So let's look at some examples. Negate the following, and I have a couple statements. So using what we now know about negation of quantifiers, these are quantifiers because they state how many exist. Go ahead and pause this, negate these statements, try it, come back, and then check your work. You might have chosen some different wording here for these sentences, but as long as it's pretty close to the same, and I'll try to mention some more as I'm going through them, you should be okay. So for the first statement, some dogs have tails, the negation would be no dogs have tails. And then remember that if the initial statement is true, then the negation would be false or vice versa. So maybe we could say define tails as like a full tail, because some dogs have a docked tail. And so we'll just say the dogs with a docked tail have no tail. Anyway, that may kind of help figure these out. But if I say some dogs have tails, that's a true statement. And then the negation would be no dogs have tails. Well, that's false, because I can find some dogs who have tails. My two dogs don't have tails, but I do know dogs who have tails. And then for part B, all dogs have tails. You could say some dogs do not have tails, or you could say not all dogs have tails. Both those would be okay. Last one, no dogs have tails. You could say some dogs do have tails. So let's go down here, decide whether the statements are true or false. Oh, we have learned about types of real numbers in a previous video. So this is going to get you're going to have to recall some of that information to try these, but I want you to go ahead and try these. Pause this, try these, come back and check your work. Okay, I did draw a little Venn diagram to kind of help as I was working through these. If you remember this from my previous video, the natural numbers were the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, goes on to infinity. Whole numbers include the natural numbers plus 0. Integers include the whole numbers plus negatives. Rational numbers include all of those. So that's kind of the layout here. So we have the first statement, every whole number is an integer. That's true because all the whole numbers live inside the integer set. So every single whole number that I would list is also an integer. That's true. And then the second one, every integer is a whole number. So we've kind of flip-flopped this statement, and we're trying to see if I picked an integer, does it count as a whole number? Well, if I picked -5, that's an integer, but -5 is not a whole number. So this is a false statement. Next one, every natural number is a whole number. That's true because the natural number set lives inside the whole number set. And then there exists a whole number that is not a natural number. That is true. The whole number, there's one whole number that's not a natural number, and that is 0. And then the last one, all rational numbers are real numbers. That is true. They all live in the real number set. So that's all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know. I'd be happy to help. See you in the next one.